Alright, good night to those who are here. If you can hear me, just put a thumbs up in the chat. If you can hear me, just put a thumbs up in the chat so I know I can start and that you're hearing me. So we're waiting for some more persons to join, and then I will start officially. Great, I'm seeing the thumbs up. That means you're hearing me clearly. Alright, so I'm Mr. Waite. I'm a physics teacher at Anchovy High School, and tonight we will be doing a practice paper, and that practice paper will be focusing on January 2025. I hope you've been studying so far. It's better when you study first and then you come to the session, and then while I do the questions you should be able to follow along. Alright, so let's go to the first question. Alright, so this is our first question that we're going to be attempting, and as you can see, first question is on the topic of transformers. Now, you should have done transformers in the electronics and electrical topic, that's electromagnetism topic, and we know that a transformer is a device that we use to increase or decrease the voltage of an input signal. Alright, so let's fill out this section. So it says here that transformers can increase or decrease the voltage. So we should have voltage here. And if the voltage is increased or decreased, that means we have a corresponding decrease or increase in current. Alright, it follows the basic principle behind the working of a transformer is the phenomenon of electromagnetism, and we talk about electromagnetic induction. So the name of the phenomenon is electromagnetic induction. So we would just write here electromagnetic induction. And once you see the word induction, it means that something is being transferred without touching it physically. So that would give you your 3 marks. On to the next part of the question. And remember that the first question in your exam will always be a graph question. So even though you have an introductory here, that means a graph is coming up. So here we have an experiment, and in the figure it shows an AC voltage being supplied at V1, right, and it drives a primary winding of an ideal step down transformer. So an ideal transformer is one that is 100% efficient, meaning that it does not lose any energy or power. So we assume that whatever power we input will get back out that power. So let's look at the experiment. So here we have a setup of the transformer. So this is the transformer in the center here. and we have a primary coil, right? So this is our primary coil and this is our secondary coil. Now we can see that on the primary coil we have many turns, right? So those loops there represent turns, and in our secondary coil we only have 3 turns. Now this will determine the output of the transformer. When we compare the primary turns and the secondary terms, it will tell us that it's either a step up or step down transformer. So this is called a step down transformer because we have more primary turns than we have secondary terms. So that's why we refer to it as a step down transformer. So the table shows the values obtained from V2 when V1 is varied from 0 to 80 volts. So very important statement here. So we notice that V1 is the one that is being varied, and here we are asked to plot a graph of V2 versus V1 using the information in the graph. Now when we are plotting graphs, we always know that we have our responding variable on our y-axis and our manipulated variable on our x-axis. Now if you look at which of the voltages are being manipulated, it would be V1, which means that on our x-axis we should have our V1, right? So that is what is being manipulated from 0 to 80. However, what is being measured is actually V2, and so on our y-axis we should have V2 on the y-axis. So we're going to now go to our graph sheet and we're going to plot the values that we have here. So let's go to the graph sheet. So on the graph sheet here, we're going to label which one should go on the y-axis. So we said that the y-axis we should have V2, so V2 on the y-axis, and on the x-axis we should have V1. So we're going to label our axis, so we know that this is our y-axis, and so we should have V2 on this axis, and on this axis we should have V1 because that is our manipulating variable. Alright, after we have labeled our axis, we need to determine which of these boxes we are going to be using. Now my recommendation is that you use 2 boxes to represent 1. So on my x-axis I'm going to mark off 2 boxes each time. I'm going to mark off 2 boxes each time before I do my scale. So here I have 2 boxes here, 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 and 2 boxes here. And I'm going to do the same thing for my y-axis. So you're going to mark off, so let me zoom in so you can see. Alright, so I'm going to mark off 2 boxes each. So you have to do this when you are doing your graphs. So mark off 2 boxes each all the way up. Alright, now we can figure out our scale. So for our x-axis, we note that the largest number for our x-axis, which is V1, here is actually 70. So that means we should be able to go up by 10 on our x-axis. So this is our 0 mark, and so 10, 20, 30, 40, 50, 60, 70. Alright, so should be able to go by 10 there. Now if you look on our y-axis, you notice that it's not easy for us to find a a value to go up by because of how the numbers are, and that's because these are our measured values. So the measured values don't go up by a particular number, and so we have to use our scale equation to find out how much we should go up by on our y-axis. So if you note in the data, the largest number is 10.7. So what we're going to do, we're going to be using the formula to find the scale. So we're going to take the largest number and we're going to divide that largest number in our data set, and we're going to divide it by the number of divisions on our y-axis. So I need to count how many divisions I have on my y-axis in order to find out my scale. So here 2 boxes represent 1 division, so I'm going to count 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 divisions on my y-axis, so that means I'm going to divide the largest value by 10. And so if I divide the largest value by 10, my answer will be 10.7 divided by 10. And so my scale that I will use on my y-axis should be 1.07. Now, even though we get 1.07, this is not a number that we can count up by easily. So the best thing we can do is to round this number up to a value that we can count up by easily. So instead of using 1.07, which is a very hard increment, we're going to be using 1.5 instead. So this number is not very far from 1.07, right? And it will help us to get our scale. So we're going to be using 1.05. So 1.05 plus 1.05, that's going to be 3.0 plus 1.05. Sorry, that's not 1.05, that's 1.5 plus 1.5, that's going to be 4.5 plus 1.5, that's going to be 6.0 plus 1.5, that's 7.5, and so this is going to be 9, right? Plus 1.5, that's going to be 10.5, and plus 1.5, that's 11.5. No, not 11.5. That's 12. So that's 12 plus 1.5, that's 13.5. Now, using this, we know that all our values for y, all these values for y are able to hold on our y-axis. So now we can go ahead and plot the points from the graph, from the table, sorry. So first point is 0, 0. So we're going to plot our first point, which is 0, 0. So when we are plotting our graphs, we use a dot with a circle, or we use an X. So I'm going to start with a dot with a circle, so 0, 0 will be right here. And our next point here is 10 and 1.5. So 10 and 1.5. Then our next value is 20 and 3.1. So 20 and 3.1. Now 3.1 must be between 3.0 and 4.5. But how do we know which one of these markings is 3.1. How do I know which one of these markings will be 3.1? So for that, we need to work out our smallest division. Now, how do we work out our smallest division? Is how we work out our smallest division. So what do we do is take our increment, which is 1.5, right? And we divide it by the number of divisions in between 0 and 1.5. So the number of divisions in between 0 and 1.5 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 divisions in between 0 and 1.5. So when we divide our 1.5 by 10, that means our smallest division on our y-axis is going to be 0.15. So that's the smallest division on our y-axis. So with this information, we are able to find out where we can find 3.1. So all we have to do is to find back our 20, and then the next point after 3.0 would be 3.0 plus 0.15, which gives us 3.15. That means the 3.1 will be between 3.0 and 3.15. So we'll put our mark right there, put our circle, and we move on to our next point, so which is 30 and 4.7. So 30 and 4.7. So we have 30 on the x-axis and 4.7. So how do we find 4.7? So 4.7 must be between 4.5 and 6. So we're going to apply the same thing. We use our smallest division, and we're going to add 4.5. We're going to add 0.15 to 4.5 until we get to 4.7. So how many blocks will take us to 4.7? So if I just use my calculator here, you will see that if I start with 4.5 and I add 0.15, I get 4.65. So that means I need to add again plus 0.15, I get 4.8. So that means our marking for 4.7 has to be between, so first box, second box, so 4.8 is the second box, so it's in between the first box and the second box. So it would be 4.7 would be somewhere in between the first box and the second box. Alright, so that with a circle, and we go back. So we have done that one. So next we're going to find 45 and 6.7. So 45 and 6.7. So 45 would be halfway between 40 and 50, and we go up to 6.7. So we're going to do the same thing. We're going to be adding 0.15 to 6 until we get to 6.7. So all you need to do is clear this. So we're adding 0.15 to 6. That's going to give us that plus 1.5 plus 1.5. So let's see how much that gives. So that gives us 6.45. So the third block gives us 6.45. So we need to continue adding plus 0.15. That gives us 6.6. That's at the fourth block plus 0.15. That gives us 6.7. So that means it takes us 1. So 4 point. So we're gonna get 45, right? And we see where the fourth block will give us 6.5. So in between our third and fourth block, we should have our 6.5. So in between our 1, 2, 3, third and fourth block, we'll have our 6.5. Oh, it's actually 6.7. So 6.7. Alright. Then we have 60 and 9. So that one is easy. So we find 60. Right. And we carry it all the way up to 9. So 60 and 9. Alright. And the final one is 70 and 10.7. So 70 and 10.7. So 70 is this line, and 10.7 will be somewhere in between 10.5 and 12. So all we need to do is add 10.5 plus our smallest division, which is 0.15. So that gives us 10.65. And remember, now we want 10.7. So if we add 0.15, which is our smallest division, again, we get 10.80. So that means 10.7 has to be in between 10.65 and 10.8. So that's in between the first and second block. So the first and second block. So it's not the first block, but in between here. And we would have completed all our points. So all we have to do now is to put in our line of best fit. So I hope we were following just now, and if you understood what just took place there, you can just give a thumbs up in the chat, as I will put in the line of best fit now. So line of best fit should be a line that goes through as many points as possible and follows the trend of all the points. Alright, so my line of best fit is that line. And so we're going to add our title. So one important element of our graph is the title. So we're going to add our title. So graph showing. And what is the graph showing? It's showing V2 versus V1. So V2 versus V1. Right, and we're going to add our scale as well. So the scale for our graph here would be, so the scale for the graph, so for the y-axis, every 2 centimeter block we're going up by, so every 2 centimeters we're going up by 1.5 volts. And for x, for every 2 centimeter we're going up by 10. So for every 2 centimeter, we are going up by 10 volts. Alright, so we have our scale, we have our title, and our title should be underlined. Right, we have labeled our axes, and we have our line of best fit. So with all of that information, you should be able to get your 7 marks for the graph. Should be able to get your 7 marks for the graph. Alright, so we're going to move on now to the next part of our question, which is to find the slope of the graph. So the slope here just refers to the gradient of the graph, and so we know that in order to find our gradient, we need to select 2 points on the line of best fit that are far apart. So some teachers would say you would create a large triangle, and it's the same thing. So we're going to do now, we're going to select 2 points that are not plotted, and they should be far apart. So I'm going to be using this point right here. So let's use this point right here. So I'm going to be using a different color and a different symbol for our points here. So I'm selecting this point on the line of best fit, right? And I'm going to select another point that is far apart. So let us select this point right here. Right, select that point right there, and then we zoom out, and now we're going to label our points. So this is going to be called P1, right? I'm going to call this P2. So in order to do our gradient, we need to find the coordinates of these 2 points. So we're going to find the coordinates of the 2 points. So for point number 1, our coordinate here is going to be that point on the x-axis along with this point on the y-axis. So for P1, you must have a x value, and so that's going to be x1 and a y1. So for this, the x value is 15. It's midway between 10 and 20. And our y value is halfway between 1.5 and 3.0. So if I should take the smallest division, which is 0.5, and I multiply that by 5, that will take me halfway, and then I add that to 1.5. That means halfway between 1.5 and 3 is 2.25. So this mark here is 2.25. And another way you could do this is to just add 0.15 to 1.5, right, until you get to the halfway mark there. So you need to add 0.15 5 times to get to the 2.25 mark. So we have our coordinates for the first point. Now we need our coordinates for the second point. The coordinates for the second point will represent our x2 and our y2. So what is our x2? So we'll just take this mark and we bring it all the way down here. So that means x2 is 65. So that means x2 is, just get rid of this. So x2 is 65, and y2, so what we're going to do, bring across this point, right, and it's going to be the first mark, 6th mark after the 9. So all we can do to get this, once we know our smallest division, right, we can just have our smallest division, which is 0.15, multiply that by 6, and we get 0.9, and then we add that back to our 9.0. So plus 9.0, and we get 9.9. So that means our y value here is 9.9. Now we have all that we need to calculate the gradient, so we can go ahead now and calculate our gradient. So we know that the gradient of a graph, or S, the slope, is going to be equal to y2 minus y1 over x2 minus x1. So we're now going to be adding the values. So y2 here is 9.9. So y2 is 9.9. So we have 9.9 minus our next y value, which is y1. So y1 was 2.25. So 2.25, and we divide that by our x values. So what was x2? x2 was 65 and x1 is 15. So x2 is 65 minus x1, which is 15. And so we just clean that up. 9.9 minus 2.25. 9.9 minus 2.25. That gives us 7.65. So we have S being equal to 7.65 divided by 65 minus 15. That should give us 50. Alright, so that's 50. So that means our gradient is going to be 7.65 divided by 50, which gives us a gradient of 0.153. So I'm going to round that to 2 decimal places. So the answer is 0.15. Right? And since both axes are in volts, the units cancel, and so there are no units here for our gradient. Now the next question says, what does the slope of our gradient represent? So since it is a graph of V2 versus V1, that was what we were supposed to plot. So if we go back to our graph, we plot a graph of V2 versus V1, right? So they're asking us, what does the gradient of this graph represent? What does the gradient represent? Now, if you remember the formula that we use in ID transformers, you remember that V2 over V1 is equivalent to the number of turns N2 over number of turns in the primary coil. So that means if we find the gradient of this line, we're actually trying to find out the ratio of the turns, right? So what we're going to be writing here is that the slope represents the ratio of the, and this would, so since it says V2, right, it would be the secondary terms. So ratio of the secondary turns to the primary turns, or vice versa. So our slope here represents the ratio of the turns. Now our next question said we should use the graph to determine the value for V2 when V1 is 50. So the fact that the question says use your graph, it means that you're going to go back to your graph. You're going to find V1, which is 50, right? And then you're going to bring it to your line of best fit to find V2. So going back to our graph, right, we're going to be finding the value that corresponds with 50. So when V1 is 50, right, what is the value of the graph. So here, if we should bring it across, right, bring it across, we get a value of 7.5 plus our smallest division here, which is 0.15. So that means we were gonna get a value of 7.65. So the corresponding value to 50 here, based on the graph, is 7.65. So that's what we'll put for our answer. So I have 7.65 volts as the answer. Moving on to our next question. So next question asks us to calculate the current I2 in the secondary winding when V1 is 50 volts. So based on our knowledge, we should know that there is an equation, V is equal to I times R. So if you remember Ohm's law equation is this equation. However, it asks us to calculate the current in the secondary winding. So that means we need the current in the secondary winding, and we should also use the voltage in the secondary winding. So you're not going to use the voltage of the primary winding because you're trying to find the current in the secondary winding. So you're going to use the voltage in the secondary winding and the current in the secondary winding, right, in the equation. And so since we need to calculate the current, we're going to transpose this equation. So that means I2 is going to be equal to V2, right, divided by R. And so I2 must be equal to 7.65 volts divided by the value for the resistance in the question was, you can see right here, the value for the resistance is 5 ohms. So we need to add our 5 ohms. So 5 ohms. And that means the current is going to be 7.65 divided by 5 ohms, which will give us a value of 1.53. So our current is going to be 1.5. I'm running off to one decimal place here. So 1.5 amps, and I did it to 1 dp, one decimal place. So that is the value for our current in the secondary winding. So I hope we are following so far. So if you're following so far, you can just put a thumb in the chat as we move on to the next question. So the next question here says we are supposed to use a particular equation to find out what I1 is. So in the previous question, we'd have calculated what I2 is. So I2 is actually 1.5 amps. So let me just indicate that right here. So I2, we calculated I2 to be 1.5 amps, right? And so they asked us to find I1. Now we know that we already calculated the slope, which is S. And the slope that we calculated, which is the gradient, is 0.15. So that means slope is 0.15, right? And we are now to use that information to find I1. So all we need to do is substitute in our values, right? So I1 is going to be equal to S, which is 0, or gradient, 1.5, times I2, which is 1.5 amps. So our gradient is 0.15, and our value for I2 is 1.5. So that means our I1 is going to be 1.5 times 0.15, and our answer here is 0.225. So answer here is 0.225 amp, or you can run it off to 2 decimal places since gradient has 2 decimal places, so 0.23 amps, and arrow is to 2 decimal places, so 2 BP. Alright, and that will give you your 2 marks. Alright, next question asks us to calculate the power dissipated in the resistor. So we need to find out what's the power that is dissipated in the resistor. So there are more than one ways you could use this information here. And so because our resistor is in the secondary part of our circuit, that means we're going to be using the information for V2. We can use the information for V2, right, to calculate the power. Now if you remember, there are various formulas for power. So power can be equal to I times V, right? Power can also to be equal to I squared times R, right? So any one of these formulas will get us the answer. So since we already found out the current that is going through the resistor here, right, that would be I2, we can use that information along with the information for the resistor to find out the power. So let's try that out. So our value, so we're gonna be, so it's gonna be P. So let's zoom in. So power in the resistor, which is in the secondary part of our circuit, is gonna be equal to the current I squared times R. So the power in the secondary coil is going to be equal to the current squared, which is I2. So I2 was 1.5 amps, so it's going to be 1.5 amps squared times 5, which is the resistance, so 5 ohms. So that means the power will be equal to 1.5 squared, so 1.5 squared times, and the resistor is 5, so our answer is 11.25 watts. So our answer here is 11.25 watts. Alright, I hope we are following. If you are following, you can just drop a thumbs up in the chat so I know that you are following, or you can ask any questions wherever you have a question. Alright, now next part of the question asks us to determine the input power to the primary winding by the source. Now if you notice, we have calculated the power for the secondary winding, and because the question said that we are looking at an ideal transformer, for ideal transformers the power that is provided must be equal on both sides. So what that means is that energy is conserved. So for ideal transformers, we know that the power in the primary coil is equal to the power in the secondary coil. Therefore, if the power in the secondary coil is equal to, so we just write a statement here, since the power in the secondary coil is equal to 11.25 watts, then the power in the primary coil must be the same, because the power or the energy must be conserved. So it's 11.25 watts as well. And once you would have been following all of that, then you would have gotten your 25 marks for this question. All right. So we're going to move on now to our next question. Right, so next question here is under the topic of energy. So it says that we're supposed to identify one alternative energy source utilized in or that is relevant to the Caribbean, and one of those that we know must be relevant to the Caribbean is solar energy, because we receive a lot of sunlight based on our location. So solar energy is an alternative source of energy that we use in the Caribbean because of our geographical position. Next question says that we should state two ways in which alternative energy we're to state two ways in which alternative energy sources like the one mentioned in the question above can be important to the Caribbean. So one of the first things about solar energy is that it reduces our dependency on fossil fuels. So the first reason you want to state here, number one, is that it reduces our dependency dependence on fossil fuels. And if it reduces our dependence on fossil fuel, that means we will import less of that, which is economically good for us. And the next thing about solar energy is that it is environmentally friendly. So it is environmentally friendly. So that means we have less emissions. So this reduces greenhouse gases. Greenhouse gas emissions. All right. So that will get us our 2 marks. Next question asks us to state the law of conservation of energy, and this is a simple question here. So we know that it states that energy cannot be created, or destroyed but can be transformed. So it can be transformed from one form to the from one form to another. All right. So once you have that, all those 3 elements, right, you will get the 2 marks there. Next question is a scenario. So it says a motor vehicle is traveling along a level road What are the main, so the key term here is main, what are the main energy changes taking place when the vehicle comes to rest after the brakes are applied? So if the vehicle is traveling along the road, that means it possesses kinetic energy, right? So it possesses kinetic energy or kinetic energy. And so when the brakes are applied, what will happen is that this kinetic energy will be converted into thermal energy. Thermal energy plus sound. So that's where you will hear. So thermal energy plus sound. So the reason why we have a plus here is because they are both happening at the same time, right? So that's all you need for the 2 marks. So you can write the energy transformation diagram, use the energy transformation diagram, or you can write it in words. So kinetic energy is being transformed into thermal energy plus sound. Alright, moving on to the next part of our question. So here's the next question here. So it says an elevator raises a group of 12 persons to a vertical height of 10 meters in 5 seconds. If the average mass of persons in the group is 55 kilograms, then we should calculate the gravitational potential energy by the group. So you have to look carefully at that, by the group. Now we know that gravitational potential energy, or the change in gravitational potential energy, is equal to m times g times the change in height, right? And in the scenario, we are given the change in height, right? We are given the mass, the average mass. So the average mass of persons, so that means the average mass per person is 55 kilograms. So that means we would need to find out what the total mass is in order to work out this question, and they've given us G in the question as well. So let us first work out the total mass. So if one person has an average of 55 kilogram, that means for 12 persons it's going to be 12 times 55, right? And 12 times 55 is equal to 660, right? So 660 kilograms. So that means for 12 persons, right, it's 660 kilograms. That means our change in gravitational potential will be equal to 660 kilograms times g, which is 10. So that's 10 meters per second squared, right, times the change in height, which is 10 meters, right? And so our change in potential is going to be equal to this number times 10 times 10. So that's going to give us 66000. And you know that is going to be in joules. Alright, if you're following, just put a 1 in the chat if you got that question a while ago. Just put a 1 in the chat. Got that question. That's going to be your 4 marks. Now if you don't calculate the total mass, you're going to lose marks from the question. If you don't calculate the total mass of the 12 persons. Alright, moving on. Now we're asked to find the power required to raise the group, right? Now another formula for power, so now we're not dealing with circuits, but we're dealing with a group of persons being lifted through a height. So another formula for power here would be equal to the work done, or energy, right, divided by time. So energy divided by time, and we have already found the energy here, right? So the power is going to be equal to the 6,000 joules of energy divided by the time, which is 5 seconds, and time must always be in seconds when you're using this equation here. So the power is going to be equal to 66,000 divided by 5. So this was times 100. So we're going to divide that by 5, and our answer is 13,200. So 13,200 watts of power is required to lift these persons through that height of 10 meters. Alright, and you would have actually completed the next part of the question 2. So we're moving on to question 3, and this is going to be the last question for tonight. I will do question 4 to 6 in the next session. So let's conclude the session with question 3. So here, question 3 is on the topic of thermal energy. So this is from the nature of heat topic, right? So first question here tells us that the effects of thermal expansion can be observed in many everyday situations, and we are to list 3 observed examples of the effects of thermal expansion. So would somebody like to give me one of this? So just give me one observed example of thermal expansion. So I know you must have studied this. So I'm just looking in the chat now to see who will get a 1 or 2 or a 3 mark from this question. What are some everyday examples or observed examples of thermal expansion? You can put your answer in the chat. Alright, so let's go. So number one example is that the gaps that are left between railway tracks, right? That's one example of the effects of thermal expansion. So gaps are left between railway tracks. To prevent damage when heated. So that's one example. Another example of thermal expansion is a ballistic strip being bent in a thermostat. So a ballistic strip, and not ballistic but a bimetallic strip, and bi means 2, so 2 metals are joined together and they expand at different rates, right? So a bimetallic strip bending when heated in a thermostat. So a thermostat is just a device that we use to control the temperature of an environment. And then finally, if you observe a thermometer, you realize that it utilizes the concept of thermal expansion in order for us to measure temperature. So what we can put here is expansion or you could say increase in volume of liquid in thermometers. So expansion of liquids in a thermometer. Alright, so the expansion of liquids in a thermometer, that is also an observed example of thermal expansion. Alright, let's move on to the next question. Next question here asks us to indicate where will be an increase or a decrease in temperature in the following scenarios. So for this question, you need to have a good grasp of the kinetic theory of matter, right? So there is a relationship between the kinetic energy, thermal energy, and the temperature of a body. So let's look at these situations. So the first situation here says that Samara turned on an oven to roast a breadfruit. More thermal energy enters the breadfruit than the energy that leaves the breadfruit. So if we have an increase in thermal energy, that means we have also an increase in temperature. So the relationship is that when there is an increase in kinetic energy of particles, so if we look at the kinetic energy of particles, once there is an increase, there will also be a proportional increase in the thermal energy, right? And if there is an increase in thermal energy, that means that there is a proportional increase in the temperature, right? So that's a relationship. So an increase in the movement of the particle will cause us to have more thermal energy, and if there's more thermal energy, that means we will have an increase in temperature. So for this one, we can say that there will be an increase in temperature. Alright. Next one says Aisha lights a candle during the night time in the month of December, and the windows are open, and so a great amount of cooler air enters the room than the warmer air leaving the room. So that means there is a imbalance between the amount of cool air and warm air. So we know that warm air has more thermal energy than cool air. However, when we combine those together, we know that if we have more cool air entering than warm air, that means that the thermal energy will decrease. And so if the thermal energy decreases, then the temperature will also decrease. So there will be a decrease in temperature. Alright, so that's that. Let's see what else we have here. Alright, so this question here is on thermometers, so still on thermometers. So that's one topic that you need to be very versed on. So here it asks us to identify the physical property that is being used in the following thermometers. So we're identifying the physical property, and a physical property, right, really refers to a physical quantity that we can measure. So anything that you're going to be stating here must be related to a physical property or a quantity. So for a thermocouple, right, that's a type of thermometer. It is used to measure temperatures of an oven. Now, in order for us to measure the temperature using a thermocouple, there is a physical property that changes with temperature that we use for this thermometer. And the name of that physical property is the EMF, otherwise called the electromotive force. So that's the electromotive force. So the electromotive force is what varies with the temperature, right? And another name for electromotive force, we can also refer to it as the voltage, right? So EMF or voltage, whichever one you have, will get the answer correct for that. The next one is a liquid in glass clinical thermometer, right, which is used to take the temperature readings of a sick child. So we use that to measure the temperature of human beings. So what is the property that varies with temperature here? So for this one, it would have to be the volume of the liquid. So the volume of the liquid inside the thermometer expands, and so with the expansion of the volume of the liquid, then we can get a corresponding value for the temperature using the scale on the thermometer. Alright? If you are still following, just leave a 1 in the chat. We're almost at the end. So if you're still following, just leave a 1 in the chat. Alright? So we're on to the final question. Now this question is a gas law question. So it asks us, so it says our weather balloon is deployed to observe and send information about the makeup of a volcanic ash plume that were emitted from this volcano here in St. Vincent. And it says that we are given, the balloon has a volume of 28 meter cube. So that is our initial volume. So that's what's going to be V1. So V1 is 28 meter cube. And then we have, it says the gas inside the balloon is heated from 176 degrees Celsius. So that's going to be T1. So that's going to be 176 degrees Celsius, right? And it is going to be heated to T2, which is 240 degrees Celsius. And it says here that the pressure inside the balloon is constant, and we are to determine the new volume, which is going to be V2, right? So V2 is what we want to find out. Now, if you don't remember which equation to use for this, all you need to do is to write back the general equation. So for this, we are going to need, so let's write the general equation, combined equation, which is P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. Right? And because the question says that the pressure inside is constant, then we can eliminate the pressures from the equation. So that means our equation to calculate the answer will be this equation. So it's going to be V1 over T1 equal V2 over T2. Now, in order to use this equation, we know that we're dealing with absolute temperatures, and absolute temperatures must be in Kelvin. So in order to convert, we know that we should do what? We should actually add 273 to each of the values to get it to Kelvin. Right? So when we add 273 to each of these values, we should get it to Kelvin. So our first value here, which is 176, right, plus 273, is going to give us a value of 449. So that's 449 Kelvin. Our next value here is 240 plus 273. So 240 plus 273. That should give us an answer of 515. So 515, that's what I saw. No, 513. So 513 Kelvin, right? And once we have our units in Kelvin, then we can go ahead and plug in the information for the equation. So adding the information to the equation, we don't need to convert the volume, right? So it's going to be 28, right, divided by T1, which is 449, right, equal, not equal, yes, equal, V2, which is what we don't know, divided by 513, right? And so in order to find out V2, we're going to transpose the equation here. So we're going to multiply each side of the equation by 513. So multiply this side by 513, right? And we multiply the other side by 513. So 513 times 28, all divided by 449, will give us the value for V2. Right, so this cancels out that, and so our answer will be 513 times 28. So this is times 28, and we divide that by 449. So 449, and our answer there should be answer there should be 32. So if we round it off, V2 is going to be equal to 32 meter cube, and that would be our answer for our volume, new volume. So the volume has to increase as well as the temperature increases. Alright, let's see what else we have here. Alright, so this is the last part of the question. It's another situation here. So it says here, in another situation, the volume of the balloon was kept constant and the pressure of the gas was allowed to change from its initial value of 1 times 10 to the 5th Pascal, right? And now we're asked to calculate the new pressure if the temperature of the gas increases. If the temperature of the gas inside the balloon was heated from 176 to 240. So we're using the same temperature, right? However, now what is kept constant is the volume. So what is kept constant here is the volume. So again, all you need to do is write back your combined equation, right? Write back your combined equation, right? And whatever is constant, right, you're going to eliminate it from the combined equation. So volume is constant here, right? And so the equation that we will use is P1 over T1 is equal to P2 over T2. Now what are our values for P1? So P1, the initial value, initial pressure here is equal to 1 times 10 to the 5th Pascal. We are asked to find the new pressure, so that is P2. That's what we are trying to find. And we know that the T1 is 176, and we already converted that to Kelvin. So that was 449 Kelvin. So T1 should be 449 Kelvin, and T2 should be, based on our last calculation, 513. So 513 Kelvin, right? So all we need to do now is plug in all this information in what we have over here. So P1 is going to be 1.0 times 10 to the 5th, right, divided by T1, which is 449, equals to P2, which is our new volume, divided by 513. And we use the same procedure, so we're going to multiply each side by 513, right? Multiply this side by 513. 1 times 10 to the 5th, right? All of that divided by 449 is going to be equal to P2. So all we need to do is to put that in our calculator. So let's clear this. It's going to be 1.0 times 10 . So 1.0 times 10 to the 5. That's times 513. That gives us, oh, it's a maths error. So let's do it this way. So 1.0 times 10 to the 5. Oh. Let's go back. 1.0 times 10, right, to the 5, and that times 513. That's what we get. All right, and then we're gonna divide that by 449. So divide that answer by 449, and our answer should be number there. So it's 144,253 or 254. So the pressure here is going to be, and I can 253.9 pascals, and this in standard form would be 1.14 times 10. So if we should move the point, right, 1, 2, 3, 4, 5 times, so that means it's going to be 1.14 times 10 to the 5th pascals for the answer. Right, so that will be our answer for that question. All right, last question now. It asks us to find the percentage increase in pressure based on our information here. So how do we find our percentage increase? How do we find our percentage increase? So percentage increase is very simple. So the percentage increase will have to be equal to, you're going to find a change in pressure. So P2 minus P1, all divided by P1 times, since it's percentage, times 100. Right, and since P2 was 1.14 times 10 to the fifth minus 1.0 times 10 to the fifth, right? All divided by 1.0 times 10 to the fifth, and all of that by 100. So if we should work that out on the calculator, alright, so let's just subtract that from 1, 2, 3, 4, 5. That's 1.14 times 10, right, .14 times, right, times 5, right, minus 1.10 times 10 to the fifth, right, and we can syntax error. Alright, so let's just use the numbers. So we got 1, 1, 4, 2, 5, 3 minus 1, 0, 0, 0, 0, 0. That leaves us with that answer, and we divide our answer by, divide that by, right, and then we multiply that by 100, and that means our answer is 14.25%. So our answer is 14.25%. So that's the percentage increase that we observed. And we are at the end of question number 3. So in our next session, we will tackle question 4, which is on waves, refraction and reflection, right? And we'll tackle question 5, which is on circuits, right? And question 6, which is on radioactivity. So we'll see you in the next session. Have yourselves a good night and keep studying.